Hello everyone, welcome to the course Advanced Logic Synthesis. First of all, let me introduce myself. My name is Dheeraj Taneja. I work for Broadcom Technologies Hyderabad. I have been working in this industry for past 11 years now. I did my graduation from BITS Pilani in 2002 in electronics engineering. Let's first see what all we would study in this course. The objective of this course is to study the components of digital design, that is the gates, various sorts of combination and sequential gates that make up the digital design, and then learn the process of converting the higher level design which is written in an HDL like Verilog or VHDL into the gates using the process is called synthesis. So we'll start with basics of synthesis and go on to see the advanced concepts of synthesis. So this course is divided into 5 major units. Unit 1 and Unit 2 are carried over from the course VLSI design. So they are more or less a refresher course into the MOS transistor. How what are the transfer characteristics of PMOS and NMOS, how they are combined into a CMOS, and how the gates are built using CMOS. We will see basics of layout. We'll see stick diagrams which are the representation of layout. Then Unit 2 we'll study about the different logic families that make up the digital design, like NMOS logic, ratioed logic, pseudo NMOS, transmission gates, and so on. We'll also look at how do we calculate the propagation delay, or how do we estimate the propagation delay of a cell. We'll see different kind of combination and sequential logic design techniques. Then Unit 3 onwards, we would look into the process of synthesis. We'll look into what are libraries, what are different kind of views, how do we we'll also see how do we write RTL code, and what construct of RTL corresponds to what part of the digital design. Then we'll see the whole process of synthesis. Unit 4 we'll visit some advanced techniques of synthesis. Let's say you are not meeting your design constraints. What else could we do? What more can we do in synthesis to make sure that our design meets the performance goals? Unit 5 is a very interesting topic called timing analysis. This is a technique which is employed industry-wise to make sure that the design meets the performance requirements of a particular technology node. The course at the end of this course, a participant should be able to write a basic RTL code and synthesize it by setting constraints. He should be able to validate the results and analyze the different synthesis reports. He should be able to synthesize a design which has some targets like area and timing. He should be able to perform critical path synthesis if required. And then lastly, he should be able to perform timing analysis on the synthesized netlist. If time permits, we will also look at the functional equivalence, which this is the process by which we make sure that the gate level netlist that we get out of synthesis actually is functionally equivalent to the RTL. So this makes sure that whatever commands we give to the tool have the desired effect. Let me go back to the slides. Okay. And the references for this course are first of all, we'll use the Synopsys recommended course material and lectures. We'll use a design compiler and primetime user guide for units 3, 4, and 5. Then there are a couple of books which you can refer to. The most famous one of which is Digital Design by Maurice Mano, and then there's a book of Fundamental of Digital Circuits by A. Anand. The Unit 1 and 2 lecture slides are derived from the VLSI design lecture slides, which are prepared by Professor David Harris, and they are available at this link. They are freely available for download. I would recommend each one of you to download this course material. It's a very useful course material for VLSI design. Then the tentative course plan is this: the number of hours I plan to spend on each unit. So as you can see, the unit 1 and 2 combined is unit 3, 4 and 5 is the majority of the course which is expected, since unit 1 and 2 are more of a refresher material. We should be focusing a lot more on synthesis and timing analysis. That is why unit 3 and 5 are heavily loaded. Unit 3, 4 and 5 also have lab work involved, since a lot of it is should be practical in nature. The theory is a minimal part. Let's start with unit 1. Unit 1, we will I assume that everybody is familiar with the basic working of MOS transistor. But unit 1, we'll again go back to MOS transistor and just see how it works. Mostly what we are concerned about is how a MOS transistor works as a switch, since that is the functionality we use most in the digital design. So we are looking at integrated circuits, which means there are many transistors on one chip. Very large scale integration means, in today's world, it means billions of transistors on a single chip. The most popular technique for manufacturing VLSI design circuits is complementary metal oxide semiconductor, which is in short form it's called CMOS. Why is it most popular? Is because it's fast, it's cheap, and it has low power. Obviously there are circuits which are faster than CMOS. There are also circuits which have lower power than CMOS. But when we combine all the three characteristics, that is the speed, the cost of manufacturing, and the power, in all three, when combined together, CMOS scores heavily. That is why it is most popular nowadays. We'll see how to build our own CMOS chip. That is, in first part, we'll see how CMOS is used to manufacture gates, different kind of gates. We'll look very briefly into transistor layout. We will not look into fabrication in this course. We'll look the layouts are not very big part of this course. We'll just see the basics. How does the layout look like? What information does it convey? And we'll look briefly into stick diagrams, which is a paper way of doing layouts. The tools do not, the stick diagrams are not used in CAD tools, but for our own sake when we want to represent a layout on paper. Then rest of the course we see how to build a good CMOS chip using the process of synthesis and timing analysis. Let's begin with let's have a quick look at the silicon lattice. Silicon is the most popular material for VLSI designs. The transistors are grown out of a silicon substrate by method of deposition and etching. Silicon, being a group form material, forms a closely bonded crystal lattice with 4 of its immediate neighbors. The silicon, if you see the diagram, each silicon molecule is bonded to 4 nearest silicon molecules, silicon atoms, to form a crystal lattice. Silicon, it's neither a conductor nor an insulator. It's a semiconductor. Pure silicon does not have any carriers because all the 4 bonds are satisfied. There are no free electrons available. It's a very poor conductor. Group 3 or group 5 elements are added to silicon to increase the conductivity. These are called dopants. A dopant is nothing but an impurity added to silicon to increase its conductivity. When a group 5 element like phosphorus or boron is added to silicon, that it contributes an extra electron per atom and correspondingly the free electrons are available and the conductivity increases. This type of material is called n-type silicon. If on the other hand, if group 3 element is added to silicon is doped, there is a deficiency of electron which is called a hole. This type of material is called p-type. The most fundamental, the most basic circuit that can be built out of a p-type and an n-type device is a diode. A diode is a junction between a p-type and an n-type semiconductor. The current flows only in one direction. So on the n-type there is an excess of electrons. On the p-type there is an excess of holes. The electrons flow from n to p. Therefore, the conventional currents flows from p to n. So p acts as an anode and n-type acts as a cathode. So the important point I'm sure everybody knows it, but the thing to remember here is that the current can only flow in one direction from the p to n-type. Now the extension of a diode is a transistor. Now a transistor is made up of 4 terminals: gate, source, drain and body. Many times in textbooks or in many times you would see in the matter that discusses transistor, many times the body terminal is usually not discussed, but in terms of when we talk about fabrication or when we talk about the CMOS gates, this body becomes a very important terminal. Let's see how NMOS looks like. So there's a n plus. This n plus means that this is a heavily doped n region on a substrate which is a p-type material. A plus sign usually it denotes that the region is heavily doped. For example, this is the notation here says p. There is no plus sign, so that means it's lightly doped compared to the n plus region. There are 2 terminals called source and drain which connect to the heavily doped n plus region. In case of MOS transistors, the source and drains are interchangeable. You can use anything for source and anything for drain. Then there is a strip of insulator which is silicon dioxide, and over silicon dioxide a strip of polysilicon or a metal. Right now the most popular technique is depositing polysilicon. So this acts as one more terminal called gate. So if you see that the body of the device, that is a substrate, and gate are conductors. Silicon dioxide is the insulator. That is why it is called metal oxide semiconductor. Although the gate is no longer, in today's technology, the gate is no longer made of metal. It is made of polysilicon, which is a variety of silicon that is a very good conductor, just like a copper metal. Let's see the operation of the NMOS transistor. So usually the body is tied to ground. So this P substrate is at 0 volt. Now when the gate is at low voltage, there is and P type is already on low voltage at 0. The diodes P and N plus, there are 2 diodes here from the substrate to each of the source and drain. Since the voltage at P is low and there is no channel here, that both the diodes are off, there is no current flow and the transistor is off. However, there is, although, a very weak channel between the 2 N plus regions, that is between source and drain, which can lead to a very small leakage current. Now this leakage current used to be almost negligible in older technologies. Okay, by technology I mean the width of this channel. So this width of this channel is decreasing year by year. So this is now into nanometer range. So when this channel length was bigger, the bigger the channel length, the weaker the channel here. So in today's technology, this is so small that the leakage current, that is, even when the gate is at low voltage, the small current, that is the leakage current, is now significant part of the power dissipation. We will see that later when we come to the power analysis as part of synthesis. But for discussion sake, we can assume that whenever gate is at low voltage, no current flows and the transistor is off. Now, when we start increasing the voltage on the gate, the electrons in this P region, they are attracted. The negative charge is attracted to body. So what happens is that there is a channel of electrons which gets formed between the 2 n+ region because of the high voltage at the gate. This channel is called an inversion layer. Why is it called an inversion layer? It's because the material is p-type, but the carriers here are electrons, so it is called an inversion channel. This inversion channel is actually responsible for the current flow between source and drain. So now the current can flow through the n-type silicon through this channel, and we say that the transistor is on. Now a PMOS transistor is very similar to NMOS transistor. It's just that the voltages that turn on and turn off the transistor are complementary. So in p-type substrate was tied to 0. Here the n-type substrate is tied to VDD. VDD is nothing but the high voltage. The gate, whenever gate is low, the transistor is on. Whenever the gate is high, the transistor is off. The bubble in the symbol here, it indicates that it is inverted to that of as compared to NMOS. If we revisit the NMOS symbol, there is no bubble here. However, PMOS is a bubble. Now this, let's come to VDD. What does VDD mean? So VDD in 1980s, VDD used to mean 5 volts. But as the technology has decreased, the devices have shrunk in size. So a higher VDD as high as 5 volts will damage the tiny transistors. So that is why, along with decreasing technology, the VDD is also decreasing. This also results into lower power. So this line shows the progression of VDD. So right now, for most of the technologies which are in production now, use 1 volt. Some even use 0.9, 0.8 volts for operation. This is why you see the prevalence of battery powered devices. The battery powered devices are only possible because the VDD is low. If VDD was as high as 5 volts, the battery would exhaust very quickly. Now, so let's look at transistors when they are behaving as switches. So a MOS is nothing but a transistor, a switch which is controlled by the gate voltage. Since the voltage at gate controls path from source to drain, so here we see that in MOS, whenever the gate is 0, G is 0, the drain to source connection is broken and the transistor is off. Similarly, when gate is 1, the drain to source connection is the drain to source current flows and the gate is on. PMOS is nothing but complementary of NMOS. Whenever gate is 0, the transistor is on. Whenever gate is 1, the transistor is off. So here we see that the NMOS and PMOS both behave as switches whenever the voltage on gate is toggled from 0 to VDD. Let's look at the most popular and the basic device, which is CMOS inverter. Now it is called CMOS because on the top it contains a PMOS connected to an NMOS at the bottom. The source of PMOS is connected to VDD. The source of NMOS is connected to ground. This PMOS device is also called the pull-up device since it is connected to VDD and it pulls A to VDD in a particular case. Similarly, this NMOS device is called a pull down device since it connects A to ground in one of the conditions. Now let's look at the truth table. What happens when A is 0 or what happens when A is 1? Okay, when A is 1, the NMOS here, let's remember that whenever gate is 1, so the gates of both NMOS and PMOS are tied together to form A. Whenever this gate is 1 or on a higher voltage, the NMOS will turn on and PMOS will be off. In this case, NMOS being on, it pulls A to it pulls Y to 0. So that is why it is also called a pull down device. A is 1 and Y is 0, which is a typical inverter functionality. Similarly, when A becomes 0, the NMOS switches off, PMOS switches on, and PMOS switching on pulls Y to 1 or Y to VDD. So that is why PMOS is also called a pull up device. Okay, let's look at a slightly more complex gate, which is the NAND gate. So in NAND gate, in case of NAND gate, there are this is a 2-input NAND gate. So in CMOS technology, always one input will correspond to one pair of comprising each of an NMOS and a PMOS transistor. So since it's a 2-input gate, for each input you have one PMOS and one NMOS. So let's see how they are connected together. The NMOS, the pull down circuit is a series connection of NMOS. The pull up circuit is a parallel connection of PMOS. This is the logic symbol. Anything can represent an NAND gate, any of these two. Now let's look at the truth table. Whenever both A and B are 0, the pull down circuit, both NMOS are off and both of the PMOS are on. So the output is 1. Whenever any of A or B is 1, the NMOS, one of the NMOS becomes on, but since the other one is 0, the connection is never made. However, on the pull up side, whenever any of this is 0, this means 0 means that PMOS is on, and since it's a parallel connection, it pulls Y to 1. So condition A0 B1 is similar to condition A1 and B0. That is, one of the PMOS is on and it pulls pulls Y to 1. To pull Y to 0, both these NMOS should be on. That is, both A and B should be 1. So what we see here is that when the gate type is NAND, let's say, the pull down represents the complementary functionality of a NAND gate. The complement of a NAND gate is nothing but an AND gate. So the pull down circuit will be nothing is the series connection of, that is, series means AND gate is a series connection of the complement of the gate we want to achieve. We look at this concept in detail later. Let's look at one more example of the combinational gate, which is the CMOS NOR gate. Now it is just the complement of NAND gate. Here the NMOS are into parallel and PMOS are in series. So since PMOS is in series, so A and B both have to be 0 to pull Y to 1. So if you look at the truth table here, when A and B both are 0, then only these two PMOS will switch on and Y will be connected to VDD. Either of A and B being 1 or when both are 1, the NMOS turns on, one of the NMOS or both turn on, and Y is pulled down to 0. So if we notice here that the basic gates in CMOS technology are inverter, NAND and NOR. Whenever, let's say, you want to make an AND gate, what you have to do is connect an inverter. There will be an inverter stage after the NAND stage. That means a 2-input AND gate will use up more transistors than a 2-input NAND gate. That is 2 transistors extra for one inverter. So we see that the CMOS technology is basically an inverted logic. That is, all the basic gates which are lowest in area and lowest in transistor count are nothing but they are either inverters, that is inverter, NAND and NOR. These are the basic gates. All other combinational gates are made out of these 3 gates. So if you remember your basic electronics, this is the reason why NAND and NOR are also called universal gates. Okay, this is an example of a 3-input NAND gate. It is very similar to 2-input. The only difference being that one more input adds one more pair of transistors. So since it's a NAND gate, so as I discussed earlier, the pull down network will be the complement of that is, it will be the AND connection of the NMOS. That is, all the NMOS will be in series, the PMOS will be in parallel. Also, if you notice that the connections are the PMOS connections and the NMOS connections are always complementary. That is, if the NMOS is in series, the PMOS will be in parallel, and the other way around. Okay, let's look briefly at how the circuits are laid out. So whenever the VLSI design is manufactured, it is manufactured using a set of masks. What a mask means, a mask is like a photograph. Like a photograph is developed from a negative. You can say that mask is a negative from which the positive, that is the photograph or the VLSI circuit, is made out. Now the minimum dimensions of mask, they determine the transistor size, and in turn they determine the speed, the cost and the power of the circuit. There is a very important term called feature size F, which is the distance between source and drain. It is determined by the minimum width of polysilicon. It is also called the channel. It is also called channel length. Usually, it is seen that feature size improves 30% every 3 years or so. So the layout is usually is normalized using feature size, and all the design rules, that is how, let's say, how wide the polysilicon would be, what should be the minimum distance between the two N+ regions, everything is determined on the basis of the feature size F. Here we define one more term which is called lambda, which is feature size by 2. For example, for a 0.6 micrometer process, the lambda would be 0.3 micrometer. We'll see how lambda is used in layouts later. Now, for example, we see that these are simplified design rules. These are an example of design rules. For example, this is, let's say you have a metal deposition. Metal 1 and metal 2 are they are made up of same material, only that the orientation might be different and the width might be different. That is, if let's say metal 1 is being routed in horizontal directions, it might happen that the metal 2 is routed in vertical direction. So the material is same, the only thing that can differ is the width. So let's say one of the design rule can be that the spacing between two metals should be at least 4 lambda, the width should be at least 4 lambda. So these are nothing but examples of the design rules which are normalized on the basis of feature size or lambda. Let's look at Niranjan, can you pause for a minute? Okay, now let's look at the inverter cross section. That is, when the inverter is laid out and manufactured, how does it look like on layout? So as we remember, as we go back and see that the inverter is made up of a PMOS and an NMOS. So this part is the NMOS transistor and this part is the PMOS transistor. Typically, the substrate, that is the silicon wafer, is doped and with p-type material, with a group 3 impurity to make a p substrate. Since NMOS transistor needs a p substrate, the N wells, that is the N plus dope, the regions can be directly diffused here to make the source and drain of the NMOS transistor. Now PMOS on the other hand would need a N-type substrate. So on the same p-type substrate, doping is done to make a region called N well. N well is now the N well here acts as a substrate for the PMOS transistor. Again for PMOS, for source and drain we need P plus region, so they are formed here using the process of diffusion. So this as an inverter, the source of the NMOS transistor is tied to ground, if you remember. So here we see this is a metal contact. This metal, anytime we want to make a contact of the source and drain to anything, we need to connect it to a metal layer. So here we see if you see the legend, this is the blue is metal 1. So here we see that metal 1 is connected to ground. This is nothing but the source of NMOS transistor. Similarly, the source of PMOS transistor is connected to VDD, again using the metal layer. Now we go back and remember that the input to inverter is given using the gates, that is the gate of NMOS and PMOS is tied together to form the input A. So here we see that this region here in the middle is nothing but polysilicon. That is so this cross section is a vertical cross section. So this is imagine a 3-dimensional figure, a 3-dimensional layout. So the gate here and the gate here is actually connected here somewhere behind. They both are connected to form the input A. The silicon dioxide here acts as an insulator. Now the output, again both the drain of NMOS and drain of PMOS is connected together to form the output. So the input is always the gate and the output is always from the drain. The gates of both transistors connected together, and correspondingly the drains of both transistors connected together to form the output. So this is a cross section of the inverter. Now this we'll see when we see the stick. We will not see much of design rules in this course. The design rules are very specific to technology and very specific to the kind of layout. So the picture here, this picture represents the inverter layout. So this is the cross section, and this is also this is the side view, and this is the top view of the layout. So let's look at this. So the bottom part is the NMOS and the top part is PMOS. How can we differentiate? We see that the region here is N well. So a PMOS needs an N well to function. So this part is PMOS. The rail here, this rail is the metal rail. The rail here up on the top and on the bottom. So the bottom one would be, this rail would be tied to ground. This would be tied to VDD. The contacts here are source and drain contacts. So this part is both the drains are connected together, and so this on the, if you see on the NMOS side, this is the source which is tied to ground. These are the diffusion regions. Again, this drain is connected to the PMOS drain. Again, diffusion regions. Sorry, this is the diffusion region. Again, the source of PMOS is connected to VDD here. This is the way the gates are connected together. This is the polysilicon material. So the poly of PMOS and the poly of NMOS, they both are connected together. So the gates are connected. So this is the input part. This is the input part, and this is where we apply the input voltage. This is where we get the output. So the transistor dimensions are specified as width divided by length. I mean, that is this is the notation we use. So minimum size is 4 lambda by 2 lambda. If we remember, go back and see the lambda was the feature size by 2. So feature size is the minimum channel width a technology can have. Since lambda is equal to f by 2, f is nothing but 2 lambda. So the minimum width that a technology can have is 2 lambda. That is why the statement here says that the minimum size can be 4 lambda by 2 lambda. Sometimes it is called 1 unit. For example, in in 0.6 micrometer process, it would be 1.2 micrometer height and 0.6 micrometer long. Usually, to start with, we keep the width as twice of the length. So if we see again, this is the inverter layout, and the proper polarities are marked VDD, GND, A and Y. If you notice here that so the NMOS here has the minimum size, which is 4 by 2, and PMOS is 8 by 2. That is, the PMOS width is twice of the NMOS width. We'll see why this is needed. Okay, let me discuss this in short for now. The PMOS usually, for the same width and length, the PMOS is slower than NMOS due to the fact that the hole's mobility is less than the electron mobility. So usually the factor is less than 2, but we just round off and say that the PMOS is slower than NMOS by a factor of 2. So to compensate for that factor and to make the inverter balance, that is, to make sure that both the NMOS and PMOS are of similar strength, the PMOS is usually made twice. The PMOS width is twice that of the NMOS width. So that is why everywhere you will see that the PMOS is designated as 2 and NMOS is designated as 1. Always the factor is 2:1. Okay, this is so this was what we saw in this chapter was the very basic nature of the MOS circuit, how the MOS is made up of gate oxide and silicon. The functionality we are most interested in is whenever the MOS acts as a switch, since all the basic logic gates can be made out of a combination of switches. We saw the inverter layout, and this gave us an idea into how the circuit is laid out, obviously at a very basic level. Now from next chapter onwards, we'll look at how we'll also look at a bit into the transfer characteristics of PMOS and NMOS, because this will again give us insight into how the propagation delays are calculated. We'll also see how various kinds of complex gates are made out of PMOS and NMOS. Plus, we'll see also the logic families, different kind of logic families that make up the gates. This ends chapter 1. Thanks a lot. Then you can pause.